So onwards with Gödel's theorem. So let me remind you guys of where we were. So this is what we're proving. We're proving that there is no Turing machine that does the following. It runs forever, printing out sentences of our language L. Eventually, every truth gets printed out, every true sentence of L. And it never happens that our Turing machine prints out a false sentence of L. So in other words, there is no Turing machine that is able to produce all and only the arithmetical truths. Now, the way we're proving that is via a lemma, which I forgot to write down. So our lemma is that our language is powerful enough to express functions that are not computable. So functions like the halting function or the busy beaver function. And just to remind you what it means for a language to express a function, it means that there's a formula built out of the symbols of our language, such that the formula is true of numbers n and m, just in case the result of applying n to the function is m. So here's a very simple example of that. So take the successor function that just takes each number k to its successor. So that function is expressible in L because we have this formula. So whenever you plug in n and m into these positions, the result is going to be true, just in case m is n plus 1. So the condition is satisfied, so L can express the successor function. Now, once we're able to prove our lemma, then the theorem is actually very, very easy. In fact, you proved it. So the way to prove the theorem is just to note that if a Turing machine M did exist, then you could produce an evil machine that computes the halting function. And one way to do it is just to run M as a subroutine and just wait until it prints out the answer to whatever question you wanted to ask the halting function. And because L can express the halting function, it's eventually going to print it out because it prints out all true sentences. And then once it's done that, you just keep the answer to whether it halts or not, erase everything else on the tape, and stop. So if M existed, it would be very, very easy to compute the halting function, but we know that the halting function cannot be computed, so M can't exist, provided the lemma is true. So what we were doing yesterday is just working with language so that people can see why the lemma is true. Now, actually, proving the lemma in detail would be long and boring. So you guys wouldn't be left with much illumination if we looked at all the details. So here's the plan for today. So what I'm going to do is I'm going to give you a general sense of how to do it, a general sense of how to express the halting function in L. And I assigned a homework, which is the crucial bit. And I'm basically going to tell you informally how I think the homework needs to be solved. And really all I want for the homework is for you guys to redo it carefully looking at the details. And then once you guys have an informal sense of how to prove the lemma, then that'll conclude the proof of the original version of Gödel's theorem. And I'll tell you guys how to prove from that the more familiar version of Gödel's theorem, which just says that no axiomatization of arithmetic can be both consistent and complete. So I'll explain what that means and tell you guys how to prove it. OK. I say that doing this is boring, but actually, when I was an undergraduate, I thought it was the coolest thing in the universe, and wrote out the formula like in its full glorious detail, just because I thought it would be fun. So I don't know. I guess I think it's a little bit fun. So our language L contains only the symbols on the left, but we can use those symbols to define new symbols. So we saw yesterday how to define the numerals 2, 3, 4, 5, etc. It's very easy. So 2, for example, you can just define as 1 plus 1, and 3, 1 plus 1 plus 1, and so forth. Less than, so you could say that that is true. And remember, that just means by definition, so it means that that abbreviates whatever I write down on this side. It just means that there exists something such that x2 equals x1 plus that something, and that something is not 0. So you get from x1 to x2 by adding something different than 0. Oh, we also defined these guys. So the existential quantifier we define like that. And this junction we define like that, and the conditional we define like that. OK. So now let me remind you guys how I defined, well, how you defined prime. Yes. Oh, there's a question? Oh, good. Excellent. Oh, you figured it out? OK. So just to make it less boring, can anyone remind us how to define prime using either primitive symbols or symbols we've already defined, except prime?
So I'm thinking there exists some x1 such that for all x2, not x1 or not like x3 times x2 equals x1. I guess we have to say for all x3 also. Sorry.
No, this is good. This is good. OK. There's something such that you pick any numbers you want.
Yeah. And then not x2 times x3 equals x1. And x2 and x3 not equal 0 or 1. Or I guess x1 x2, x3 not equal 0 or 1.
And it's not the case that x1 equals 0, and it's not the case that x1 equals 1, and it's not the case that x3 equals 0, and it's not the case that x3 equals 1. Is that it? There might be too many negations, and there may be one quantifier too many, since we want to say something about x1. But we'll correct it. This is definitely the right idea. Yeah.
I think some of those x1s, where you have like not x1 equals 0, not x1 equals 1, should be changed to x2s.
Okay.
I don't. I mean, I might be looking at it wrong, but I actually don't think there are too many negations beyond that.
I think
there's one few. I mean, there's a negation missing. I think.
Negation missing here.
But I actually don't think there are too many negations.
Okay. Let's read it, but I'm going to eliminate this quantifier, which I think is not needed, and then let's read it like that and see what it says. So we're thinking of this formula as testing whether x1 is prime. So what does it take for x1 to be prime? Well, it means that whatever numbers you pick, if this condition is met, in other words, if the two numbers you picked are neither 0 nor 1, then it's not the case that if you multiply them, you get x1. Now, right now we have an and instead of an if, but we can correct that easily. So I think really what it should look like is something like this. So pick any numbers you want. If they satisfy that condition, then it's not going to be the case that the result of multiplying them is x1. So we can just, like I'm going to call this alpha and that beta. Then our official statement is it's like that. Yes?
But is it really necessary to have the like the if then like that? I just feel like if you just have the and, I don't see anything wrong with it. I just feel like as long as you say that x2 times x3 equals x1 and all these things are true about x2 and x3, that's kind of the same thing, and I think it's like an overcomplication to.
You might be right. You might be right. So you're thinking we put a conjunction here, and we bring this negation out, which is what you proposed originally.
Well, no, I'm just going. Yeah, I'm pretty sure that's. When you're doing the switch, you're just using the definition of the conditional. I'm pretty sure the statements are equivalent.
I think you're right. OK, good. So it was right to begin. Good. Well done. Oh, yes, a question in the back.
Is there any reason to mandate that x2 and x3 can't equal 0?
So I take it 0 would be counted as prime if they were allowed to be 0, because you can get 0 by multiplying 0 to anything. Is that, yeah. Of course, the reasons for not counting 0 as prime are kind of ad hoc, but yeah. OK, so we're able to express x as prime. OK, so that's the last one that I'll do in detail for obvious reasons. So like now you know why it becomes cumbersome and somewhat boring to do in detail. But I hope you see like the kind of trick that's used to generate these things. So let me now just tell you in a very sketchy way how to build one's way to the halting function. So the first thing to note is what I ended up with on Monday. So suppose you wanted to have a single number code a pair of numbers. So one way to do it is you could think of the pair AB as coded by this number. And the crucial thing is that if I were to give you a number that you can get to in this form, you would be able to figure out what ordered pair that corresponds to. And that means that we can define this predicate, pair, which is true just in case x1 is the pair of x2 and x3. In fact, this one is easy to do. So we just say that x1 equals 2 to the x2 plus 1 times 3 to the x3, times 3 plus 1. So our language can, in a sense, talk about ordered pairs. In fact, it can say things like, there exists an ordered pair whose second component is 7. Could anyone tell me how to say that? There exists a pair whose second component is 7. Using that notation, which we've already defined? Yes?
I'm not going to say this formally, but like there exists a number such that if you run the pair function on that number, there's another number you can put in for x2 such that x3 will, yeah.
That's exactly right. That's exactly right. So you say this. There's an x1 and an x2 such that pair of x1 and x2 is 7. And if you wanted to say there exists a number which codes the ordered pair of 7 and 14, then you could just say it like that. So we can really talk about ordered pairs. We can make general claims about ordered pairs. OK, and this is the basic tool we're going to use to take the crucial step. And this is the step that I asked you to deal with in the problem set. So the crucial step is to have the ability to talk not just about ordered pairs, but about intervals of natural numbers for arbitrary n. So finite sequences of natural numbers. And there are different ways of doing it, but one trick that I like is based on the following observation. Suppose that I give you an arbitrary number bigger than 2. One thing you can do is you can factor it. And by the fundamental theorem of arithmetic, there's going to be a unique factorization. So I give you a number k, and that turns out to be, say, 2 to the 7 times 3 to the 0 times 5 to the 2 times 7 to the 0 times 11 to the 0 times 13 to the 1. That's the number I gave you. From there, you can extract this sequence of numbers. 7, 0, 2, 0, 0, 1, which are just the exponents. And now to make sure that we don't have ambiguity, so a problem with this is that you'll have zeros all the way forward. So let's introduce the convention that if you find a 0, you take that to not code anything. And if you find something other than 0, you take it to code the number 1 smaller. So you can think of that k as coding 6, and then nothing, and then 1, and then nothing, and then nothing, and then 0. Or, in other words, coding 6, 1, 0. Daniel? Oh, OK. So I gave you an arbitrary number k, and you used it to produce a sequence of numbers. Now suppose that I give you a number k, which has the following nice feature. It's not just that you use it to produce a sequence of numbers. It's also the case that every number you produced codes an ordered pair. So I give you k and use it to produce a sequence of numbers. And say that your sequence of numbers turns out to be 2 to the 4 times 3 to the 7, and 2 to the 1, and 3 to the 6, and then you can think of the number I gave you as coding up some ordered pairs. So in this case, 3, 6, and 0, 5, and 3, 13. And now suppose that I choose a number which is even more special. It's a number which doesn't only code ordered pairs, but is such that the first elements of the ordered pairs start from 1 and are unique. So for example, you get 1, 6, 3, 6, 2, 6. So we have 1, 2, 3. We didn't skip anyone. We didn't repeat anyone. Then you can think of the number I gave you as just coding the sequence that you get from starting with the number you associated with 1, and then going to the number you associated with 2, and then going to the number you associated with 3. Yes?
Should say 5.
I should say 5. Thank you. Yes?
How did you get to k factored as those? Yeah.
So k is just a number. Yeah. And I factored it into, say, that. For example. Say that's what I got. Just those numbers. And then it turns out that A equals that, and B equals that, and C equals that. So it's like a double coding.
Sorry, is that 7, not 7 to the C plus 1, not 17 to the C plus 1?
I picked 17 just to illustrate that you might skip some primes. For a good reason, but not a reason I've explained. It's because there are certain things that are easy and certain things that are hard. And one thing that turns out to not be immediately trivial is to just talk about the nth prime. So I give you a number n, and you need to produce a formula of L that gives you the nth prime. So that turns out to be a little bit tricky. And the virtue of the procedure that I've used is that it doesn't require us to know what the nth prime is.
OK, so the way you've done it, it doesn't matter what the initial primes are that you factor k into, because they'll be ordered in this way that you can then recover the order.
Exactly. So what's nice about them is that if I give you the right number, it's going to turn out that they all correspond to ordered pairs, with their first elements giving you the order. So then, like, it doesn't matter in what order I put them in. You're going to be able to know what order to put things in at the end. So you have this long and convoluted procedure for getting from k to a particular sequence of numbers in a particular order. And that's the main trick. Like, once you can do that, you can basically do everything. Oh, maybe I'll add something to our defined symbols. So maybe tuple. So the trick I just used, the trick I just described, can be used to define a formula tuple, which is true just in case x1 is an x2 tuple. So in other words, it codes up a sequence with x2 places, of which the x3th member is x4. So you could say something like, that guy codes a 5 tuple, of which the third element is 17. So we now have that amongst our defined bits of vocabulary. OK, and now what we want to do is start using numbers to code up Turing machines. So the first step is to use numbers to code up the programs for Turing machines. And we can definitely do that, because thanks to that predicate, we can use a number, say, n, to code up some finite set of numbers, say p1 to pk. And then we can let each of these code up a tuple, which is just one Turing machine instruction. So for example, maybe p1 codes up 0, 1, 0, right, 7. Of course, right isn't really a number, but that's no problem, because we could just think of right as 1 and left as 2 and don't move as 3. So in effect, each member of this sequence codes up a line of our Turing program. So the entire sequence codes up the entire program. And it's relatively easy, though long and boring, to use this vocabulary to just define a predicate, which in effect checks that it's not just a random sequence, that it really is a sequence that corresponds to a well-formed program. So you check that each of these is a 5 tuple, of which the first element is, well, that one can be anything you want. These two need to be either 0 or 1. That one needs to be 1, 2, or 3. That can be anything you want, and so forth. OK, so now we can use natural numbers to code Turing programs. Are people happy with the general idea about that? I think that's pretty cool. So it blew my mind when I realized that. Yeah.
Doing the same trick a third time?
Yes.
Oh, wow. Okay.
Yes. And in fact, the way I think of this in practice is I start losing track of like how many times I've used the trick. I just think of numbers as tuples, and some are tuples of tuples, and there's just no stopping you once you start. Yeah.
I don't know what you mean by the third time.
Oh, OK. So remember how this worked. So I gave you some number k, which is just a number, like 44,372, and you factor it, and you get something. And then if I give you the right number, it turns out that the exponents of the thing you got are all going to be of this form, 2 to the something times 3 to the something. And moreover, they're going to be such that the thing used as the exponent for 2, in all cases, is going to form like a nice sequence of natural numbers. So then you think of that whole beast as coding a certain tuple. And we used the prime trick twice. We used it first here and then there. And then what happens here is that we use it a third time because that sequence happens at that level. So that's the upshot of what we had done before. And then each of those, in effect, codes up another sequence.
Okay, got it.
So I invite you guys to think of it this way. So once you've seen the basic fact, which is that you can use a number to code an arbitrary n-tuple of numbers, then just think of n-tuples as numbers. So like, don't worry about it. So when I say an n-tuple, you say, oh, I guess that's a number. And when I say n-tuple of n-tuples, you say, well, I guess that's another number. And then once you see that, then of course there's no problem having a number which is in effect an n-tuple, each of whose members is a 5-tuple. And that can be used to describe the program for a Turing machine. And of course, we can also use n-tuples to describe the tapes of Turing machines. So we're going to focus on the special case in which a tape is only infinite in one direction, and it's blank except for finitely many symbols, which is really all we need to do what we want to do. So suppose you have this tape, a tape that has 1 blank blank 1 1 1 blank 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 blank. You can just code that by the sequence 1 0 0 1 1 1, and then when you end, that's the indication that everything beyond that is blanks. And of course, there is some number which is going to code that tape, that sequence, so that just codes the tape. And now we can do something amazing. Now we can have a number that codes the conjunction of a program and a tape and a position for the reader and a state for the machine. What's that going to be? Well, it's just going to be a 4-tuple. It's going to be a 4-tuple where the first thing is a program, the second thing is a tape, the third thing is, say, a position of the reader, which is just a number that tells you, so if the number is 1, then you're here. If it's 2, then you're there. If it's 4, then you're 3, 4, 5, and so forth. And S for the state you're in. And then that sequence of numbers codes up state in the operation of a Turing machine. Yeah?
What was T?
T was just a number that codes up sequence which represents the tape. So that represents the program, and that represents the tape, and that represents just a position for the reader, and S represents the state that the Turing machine is in, and that's just a number. OK, so just in effect, what we have so far is we have, let me call it Turing machine Turing machine moment, I'll call it. And that's a predicate which is true if so that just says Turing machine x1, in other words, having program x1 has tape x2, reader in x3, and is in state x4. And now we're almost done. So the next thing we can do is we can take 2 Turing machine moments and have a formula that tells us when one is the successor of the other. So when you have, you have one Turing machine moment, which is a given Turing machine in a given state with a reader and a assurer in place, and the tape in a certain location. And you ask yourself, what would happen if you were to run this Turing machine one state? Well, then you would get the same program and maybe a different state and maybe a different tape and maybe a different reader position. And we want a formula that tells us when two Turing machine moments correspond to that jump. Yeah?
So I'm just wondering, it seems like it's possible to create a for-long tuple that wouldn't be possible. So, like, are we able to check that?
Yes. And in fact, one way to check it is by using the operation that I just described. So think of it this way. So suppose that you've designed this operation jump. And that's going to hold just in case x1 codes a Turing machine moment such that if that was a real Turing machine and you ran it one step, you'd get Turing machine moment x2. So it's like, that's one step in a Turing machine operation. And then what you could do is you say, well, what's a valid initial state? A valid initial state is, you just have a well-defined program. You're in state 0. The reader is in position 0. And you have any tape you want. A valid Turing machine moment is one that you can get in a finite number of steps from the initial state using jump. And notice that when I talked about a finite number of states, there I'm crucially using my ability to talk about sequences, because really a finite number of steps means there is a finite sequence such that each member of the sequence is a Turing machine moment. And for any two that are next to one another, one is the result of applying jump to the other. OK, so now we can define the halting function. In fact, can anyone say how to define the halting function using jump?
So something like, you give a Turing machine moment, and then you say, like, this thing halts if after applying, I want to say after applying jump a finite number of times it halts, but then I have to know what it means to halt, and I don't know what that is.
OK, no. That's the idea. It's actually very simple. So you just say a Turing machine with program P halts given tape T, just in case the following is true. You have a finite sequence of Turing machine moments such that every Turing machine moments has program P. So they're all Turing machine moments of that particular Turing machine. The first one starts in state 0 and tape T, the given tape.
Why does it have to start in state 0?
Because all Turing machines start in state 0. And the given tape. Consecutive members of the sequence satisfy the jump operation. So you get from each one to the next in a valid way. And the last member of the sequence asks you to go to a state that doesn't exist, because that's what it takes for a Turing machine to halt. So that's it. We have defined the halting function. And now I'm going to say it one more time. So the way that's going to work, so what that says is Turing machine x1 halts given input x2. We just say there is a sequence such that for every So what does it take for this to hold? Well, there needs to be some sequence, and all of these are going to be Turing-machine moments, and they're all going to have X as their program. So they're all going to be Turing-machine moments involving Turing-machine X. Every I is a Turing-machine moment, which has x1 as its program. A1 has x2 as its tape, 0 as its state, and 1 as its reader position. And then we just need to add two things. The first is that you always get from one to another via jump. And the last is that the final member of the sequence takes you to a state that doesn't exist. So and jump xi plus 1. Oh, sorry. And an asks to go to a state that isn't in x1. OK. That was sloppy, but I'll read it, and hopefully you'll have the general idea. So this is our halt formula, which intuitively means Turing-machine x1 halts given input x2. And the way we spell that out is by saying there is some n-tuple such that every member of the n-tuple is a Turing-machine moment. And they all have x1 as their program. And the first member of the sequence has that as its tape and 0 as its initial state and starts at the beginning of the tape. And you can get from any member of the sequence to the next one using jump. And the final member of the sequence asks to go to a state that doesn't exist. And of course, now you can see how there's so much you can do in this language. I mean, certainly it would be very easy to define the busy beaver function, too. Yes?
I don't have a question.
Oh, OK. So that's it. We've proved the lemma. And with the lemma, we've proved the theorem. So let me just state once more what the big picture is, so that that's like what you keep in the index of your mind. So you can think of Gödel's theorem as a complexity result. It's a result that says that arithmetical truth is so complex that you can't capture it with finite instruction. There's no finite set of instructions that can encapsulate all there is to be said about arithmetical truth. So there's no Turing machine that can list all true arithmetical sentences and no false ones. And why is that? Well, it's because you can say all sorts of things in the language of arithmetic. In particular, you can express non-computable functions, as we just saw. So if you did have such a Turing machine, you could use it to compute uncomputable functions, which is impossible. So it's not that hard. Now, thinking of Turing machines in this way is a relatively recent thing. So what Gödel proved looks more like this. So it says that there's no consistent and complete axiomatization of arithmetic. Here's one way of understanding what that means. It's not exactly what Gödel meant, but it's slightly simpler, and it'll give you the main idea. So an axiomatization of arithmetic is a system for proving things in arithmetic. And the idea is that you have some axioms and some rules. And you're going to count something as a proof if it's a sequence of things such that everything on the sequence is either an axiom or something you can get from previous members of the sequence employing the rules. And in order for it to count as an axiomatization, it's crucial that a Turing machine be able to determine what counts as an axiom and what counts as a rule. So the following doesn't count as an axiomatization, just the set of all arithmetical truths. That doesn't count, because as we just saw, no Turing machine could possibly tell what counts as an axiom. Or, well, it couldn't resolve the issue of which are the axioms and which aren't. So that's an axiomatization. And an axiomatization is consistent if it doesn't allow you to prove contradictions. And that's important because in any standard system, if you prove a contradiction, you can prove anything you want from it. And what one might mean by complete is that it proves every single truth. So your axiom system can be used to prove every single true sentence of the language. The reason this follows from that, as I stated it, is that if this were true, you could use it to generate that kind of truth, that kind of Turing machine. And the way to do it is very simple. So design a Turing machine that does the following. It goes one by all sequences of sentences in the language and checks whether that thing is a proof. It can check that it's a proof because of the way we defined axiomatization. It can recognize what's an axiom and it recognize what's a rule, so it can check whether that sequence is a proof. If it is a proof, then it outputs the thing at the end. It prints something, and that thing is going to be a truth. If our system was complete, using that method, our Turing machine is going to eventually print out every truth. And because it's consistent, using that method is never going to output a falsity. So if you could find such an axiomatization, you could use it to create that Turing machine. And we know that that Turing machine can't exist. So that's how you get to the more familiar version of the theorem. OK, so that's it.